Okay, so I think we are live again. Hello, everybody. Welcome back to yet another edition of Quarantine Thermo. We continue to bring you fun kind of news from the world of science, even while the rest of the world seems to be deteriorating slightly. So yeah, I mean, seeing as I have this platform, I feel kind of compelled to just say, and I hope I can say this on behalf of the whole community, that we express our solidarity with everyone who is kind of peacefully protesting for the right to not be discriminated against or killed for the color of their skin. But with that said, it's a pleasure to introduce our speaker this week. So Dr. Zoe Holmes, who is an expert in quantum thermodynamics. And she is sort of a little bit in limbo at the moment, as far as I understand. She's theoretically in Los Alamos, but experimentally, if you like, in London right now because she can't make it over to the US with the pandemic and so on. So before I hand over to Zoe, I'm just gonna sort of give a brief recap, as always, of the format. So for those of you that haven't seen one of these talks before, Zoe's going to speak uninterrupted for sort of 45 minutes to an hour, however long she likes. And then we're going to have a question and answer session at the end. So basically, if you have any questions during the talk or at the end of the talk, just feel free to write them in the YouTube chat window and I'll relay them to Zoe at the end and we'll have a nice discussion. And so with that sort of said and done, let me hand over to Zoe, who's going to tell us about some work, which I think even part of this even went up on the archive today. Is that right, Zoe?
Yep.
Yeah, which is very good timing on your
Good to have.
part. And so she's going to tell us about thermodynamic signatures of distinguishability in an optomechanical setting. Go ahead, Zoe.
Right. Yeah. Thanks, Mark, for the introduction. I really appreciate the opportunity to disseminate this research virtually to you today. Yeah, as Mark said, I am working at Los Alamos National Lab, but physically I am still in the UK thanks to Trump's travel ban. But actually, most of this research was conducted while I was still affiliated with Imperial College London and Exeter University. And yeah, the work I'm going to talk to you about today was done with Florian Mintet and Janet Anders. So in this talk, I'm going to present two new thought experiments that probe the role of distinguishability in quantum thermodynamics. And our thought experiments are loosely based on the observation that many of the key thought experiments in thermodynamics can be visualized in terms of gases of different sorts interacting with membranes of different sorts that are attached to pistons. So I'm going to start by recapping some of these classic thought experiments, framing them in terms of gases and membranes. So the clearest example of this type of thought experiment is Gibbs's thought experiment on the mixing of gases. So Gibbs showed that the work that can be extracted mixing two distinguishable gases Gibbs showed that work can be extracted mixing two distinguishable gases using a pair of semipermeable membranes. So his protocol goes something like this. So let's suppose that we have two types of gas, i.e. gases of different elementary or molecular compositions, here sketched as a green gas and a yellow gas that are confined to two halves of a box initially. We assume that the gases are in thermal equilibrium with a heat bath at temperature T. Now, to extract work from this scenario, we use a pair of semipermeable membranes. So a green membrane that is permeable to green particles but blocks yellow particles, and vice versa for the yellow membrane. So the yellow membrane permeable to yellow particles but blocks green particles. Now, we suppose that these membranes are held in place by a pair of springs that allow them to slide. So now, if you let this evolve, the green gas is going to permeate through the green membrane and exert a pressure on the yellow membrane. And the yellow molecules are going to permeate through the yellow membrane and exert a pressure on the green membrane. So the membranes will start to pull apart under these partial pressures, and the two gases will begin to mix in the volume between the two membranes. Eventually, the two gases will be pushed, the two membranes will be pushed right to the edge of the box, and the two gases will be fully mixed. And during this mixing process, each gas will have isothermally expanded to double its initial volume, performing work on the pistons in the process. So in this way, you can extract work by mixing two distinguishable gases. But of course, if the two gases were perfectly indistinguishable, i.e. they're both green gases, then you can't find a pair of semi-permeable membranes that can distinguish between them, and so no work can be extracted. In this way, so Gibbs's thought experiment highlights the importance of distinguishability for work extraction, and it does so using a pair of semi-permeable membranes. Okay, so that's Gibbs mixing. Next, Maxwell's demon. Well, Maxwell's demon could take the form of a fictitious semi-permeable membrane that can distinguish between fast-moving hot particles and cold-moving slow particles. So you could imagine a demon membrane that only lets through hot, fast particles. So only lets through the red particles but blocks the blue particles. So this would cause one side of the box to heat up while the other side of the box to cool down, which would seemingly violate the second law of thermodynamics until at least the energetic expenditure of the demon membrane is explicitly accounted for, and then you're not going to get any violations. And finally, something akin to a hybrid of Feynman's ratchet and a Szilard engine could be formulated in terms of a unidirectional transmissive membrane. That is a sort of valved membrane that only lets particles go in one direction. So here, this membrane I'm sketching lets particles go from the left to the right, but not from the right to left. Now, if you consider a single gas molecule at thermal equilibrium, well, whether the particle starts in the left-hand side of the box or the right-hand side of the box, it's going to eventually diffuse through to the right-hand side of the box, where, because it's then blocked by the membrane from going the other direction, it will exert a force back on the piston membrane and isothermally expand to fill the whole box, resulting in it doing work on the piston. Now, you could imagine repeating this protocol again and again, and that would seemingly allow heat from a single heat bath to be perfectly converted into work, seemingly in violation of the second law of thermodynamics. Well, the resolution of this apparent paradox is that if the particle and the piston were actually at thermal equilibrium and both microscopic systems as they'd need to be, then fluctuations in the motion of the membrane would prevent work from being usefully extracted in this way. Okay, so that's three classic thought experiments framed in terms of pistons and membranes. We are going to introduce a quantum generalization of this general style of thought experiment. So our key idea is as follows. We are going to consider photonic gases instead of gases consisting of atoms or molecules, as considered on the previous slide. Now, this then opens up two different possible generalizations of a partially permeable membrane. So we can now consider a beam splitter membrane and a polarizing beam splitter membrane, which are, yes, quantum generalizations in a sense of partially permeable membranes. In both cases, we are going to consider a cavity divided into two by the membrane, and we will suppose that the membrane is attached to a cantilever, which allows it to move. This sprung cantilever is going to act as our piston. Crucially, we assume that the sprung cantilever is a microscopic quantum system, so we are now working with a quantum piston. Now, we're going to use this general setup to probe the thermodynamics of distinguishability. Specifically, we are going to consider polarisation distinguishability. So we're going to suppose that all photons in one gas on one side of the cavity are horizontally polarised, and all photons in the other gas are polarised at angle theta. So by varying theta, we will be able to probe the transition from perfectly distinguishable gases to perfectly indistinguishable gases and everything in between. And yes, we can then use this framework to discuss the thermodynamics that result from playing around with the distinguishability of the gases. Okay, so that's the central idea. The outline of the rest of my talk is as follows. So I'm going to start by talking about the beam splitter thought experiment, and I'm going to show how this thought experiment can be used to highlight a signature of bosonic bunching. And then I am going to move on to talking about the polarizing beam splitter thought experiment, which I'm going to argue can be used to realise a more direct quantum analogue of Gibbs's mixing thought experiment. I'm also going to argue that these proposals can not only be thought of as thought experiments, but could also conceivably be realised experimentally in a membrane in the middle optomechanical system. And I'm going to discuss this a little bit throughout the talk, but also at the end I'm going to come back to it and try and put forward a more general sales pitch for membrane in the middle optomechanical systems, arguing that they are a fun, flexible platform for a wide range of possible experiments and thought experiments in quantum thermodynamics. Right, so let me start with the beam splitter thought experiment. the key question we ask here is, how does the energy transfer to a beam splitter piston membrane depend on the distinguishability of the two gases? And as I said before, we're going to look at polarisation distinguishability. So we're going to assume that all photons on the left-hand side are horizontally polarised, and all photons on the left-hand side are polarised at angle theta. So that is, they're in a superposition state cos theta h plus sine theta v. Now, so there is an angle theta between the polarizations of the gases on the left and the right-hand side. So if theta equals pi over 2, then all photons in the gas on the left-hand side are vertically polarised, and therefore the two internal states of the two gases are orthogonal, and the two gases are perfectly distinguishable. But if theta equals 0, then the two gases are both horizontally polarised, and so they are perfectly indistinguishable. And for theta greater than 0 and less than pi over 2, the two gases are partially distinguishable because the gas on the left-hand side is in a superposition horizontally and vertically polarised. We're going to make a couple of other assumptions about the initial state. So we're going to assume that the photons and the membrane are initially non-interacting, such that their initial state can be written in a product form. We're going to assume that the two gases on the left and right-hand side of the cavity both initially have the same photon number distribution. And this is just so the focus of the thought experiment can be on the distinguishability of the two gases, and not have it potentially hidden by other distinctions between the two gases. And finally, we're also going to assume that the average position and momentum of the membrane initially vanishes. So it's just in the centre at the beginning, and it's on average stationary. As would be true, for example, were the membrane initially prepared in its ground state or in a thermal state. Okay, so let me just go into a little bit more detail about how we model this setting. So the Hamiltonian is composed of three terms. The raw non-interacting Hamiltonian for the photonic and phononic modes, the optomechanical interaction between the photonic modes and the mechanical degree of freedom, and the beam splitter interaction between the photons on the left-hand side of the cavity and the photons on the right-hand side of the cavity. So specifically, there are 5 modes in total. So there is the left horizontally polarised mode, the left vertically polarised mode, the right horizontally polarised mode, the right vertically polarised mode, and the mechanical mode associated with the displacement of the membrane. And the raw Hamiltonian, non-interacting Hamiltonian of these modes is simply the harmonic oscillator Hamiltonian, the 5 modes. So here we set h bar equals to 1, and we do that throughout these slides. Okay, and then we have the optomechanical interaction term. So as the photons oscillate around the cavity, they will collide and exchange momentum with the membrane. And this results in a pressure, radiation pressure being exerted by the photons on the membrane. The total force exerted on the membrane is going to be the force exerted per photon, which is G, multiplied by the difference in the number of photons on the left-hand side of the cavity and the number of photons on the right-hand side of the cavity. So this gives rise to an optomechanical interaction energy of the form equal to the total force times the displacement of the membrane. And then we have the beam splitter interaction term, which is of this form. So at a rate lambda over 2, a photon on the left-hand side is annihilated and a photon on the right-hand side is created, where the two photons are of the same polarization, and so the interaction is polarization conserving. So now we want to try and calculate what the energy transfer to the membrane is, so we need to calculate the dynamics of the membrane. And to do so, we decided to work in the Heisenberg picture, as this enabled us to obtain general results for the evolution of the setting for a very general initial set of conditions. So we worked in the Heisenberg picture, which meant we had to solve a set of coupled differential equations for the phononic and photonic modes. The Heisenberg equation for the mechanical degree of freedom is just that of a driven harmonic oscillator, where the driving term is equal to the force exerted by the photons on the membrane, which is just equal to the force per photon times the difference in the number of photons on the left and right-hand side. Now, the number imbalance, so the difference between the number of photons on the left and right-hand side, is governed by this differential equation. So to solve to find the dynamics of the membrane, we need to solve the coupled differential equations given by these two equations. And to make this tractable, we decided to work in the weak coupling limit, so the regime of small g, and solve these coupled differential equations perturbatively. So this, in practice, amounts to assuming that the back action that the motion of the membrane has on the photon dynamics is negligible, which is a reasonable assumption as long as g is reasonably small, as is true for typical experimental parameters, which I'll come on to later, and also as long as the membrane is not moving around too much initially, so as long as it's close to its ground state or in a reasonably low temperature state. So with our perturbative approach, we then solve the dynamics, and this is the expression we obtain for the energy transfer to the membrane to second order in the optomechanical interaction strength G. So here we're looking at the average change in energy of the membrane, so the average energy of the membrane at time t minus the average initial energy of the membrane, and we find that it is equal to the sum of three terms. So the first term is just equal to the fluctuations in photon number initially, so the fluctuation in photon number of each of the gases initially. The second term is proportional to the average number of photons per gas initially, and the third term is proportional to the average number of photons per gas all squared times cos squared theta, where theta is the distinguishability of the two gases. So to get a sense of how this expression behaves, it is helpful to consider different possible choices in the initial photon number distribution of the two gases. So suppose you have thermal gases, so two photon gases that are initially in a thermal state. If this is a high temperature thermal state, then the initial fluctuations in photon number will be large, and so there'll be a large component to the energy transfer to the membrane that is independent of distinguishability. However, for low temperature thermal states or special non-classical states such as Box states, or even, for example, coherent states, then the average number of photons per gas can be large as compared to the fluctuations in photon number. In this case, then we have that for perfectly distinguishable photons, this cos squared term will vanish, and so the energy transfer will be proportional to the average number of photons per gas. But for indistinguishable photons, we have this additional cos squared term, which will just evaluate to 1, and so the energy transfer to the membrane will be proportional to the average number of photons per gas squared. That is, the energy transfer to the membrane is quadratically enhanced for indistinguishable photons as compared to distinguishable photons. Right, now we will argue that this enhanced energy transfer is a signature of bosonic bunching as observed in the Holmes effect. So to understand how heuristically bunching could affect the membrane dynamics, it helps to consider the simplified initial state where there are only two photons in the setup, so one either side of the cavity initially. When two photons impinge on a beam splitter, there are four possible outcomes. So you could either have the one from the left-hand side is reflected and the one from the right-hand side is transmitted, or you can have the one from the right-hand side is reflected and the one from the left-hand side is transmitted, or you can have them both transmitted, or you can have them both reflected. If both photons are transmitted or both photons are reflected, then there'll be no net displacement to the membrane. But if the two photons leave the beam splitter through the same arm, for example to the left, then the beam splitter will end up displaced to the right, and vice versa if the two photons leave to the right. Now for distinguishable photons, each of these four options are equally probable. But for indistinguishable photons, options C and D are indistinguishable, and so they destructively interfere, and you only get options A and B, i.e. the photons are certain to leave the beam splitter through the same arm, that is, they bunch together, and this is the well-known Hong or Mandel effect. Now, whether the photons are distinguishable or indistinguishable, the average displacement to the membrane will be 0. But if the photons are indistinguishable, the probability for the membrane to be displaced is twice that as for when the photons are perfectly distinguishable, and therefore for indistinguishable photons, the fluctuations in the position of the membrane, and therefore also the energy of the membrane, will be greater than in the case of perfectly distinguishable photons. So in this way, it seems as though the enhanced energy transfer can be attributed to the back action of photonic bunching on the piston due to the entanglement between the photons and the membrane, as in the Holmes effect. So yeah, the enhanced energy transfer that I showed you on the last page can be attributed to the back action of bunching, and the Holmes effect is the simple way of visualizing this. Okay, so I just thought I'd mention at this point that there's been a sort of slight revival of interest recently in the role of bosonic bunching in thermodynamics, and our work fits in nicely against this backdrop. So the first paper here argues that bosonic bunching can enhance the conversion of information and work in a Szilard type engine, and the second two papers, very recent papers, look at the power of bosonic bunching to enhance the performance of Otto engines. And I'd like to think that the simplicity of the thought experiment I've just shown you complements these other papers quite nicely by giving an intuition as to how bunching can lead to such enhancement effects. Now, as I mentioned earlier, this can be thought of as a thought experiment, but also hopefully it could actually be realised experimentally in the not so distant future in a membrane in the middle optomechanical system. So a membrane in the middle optomechanical system is simply an optomechanical system in which an optical cavity is divided into two parts by a microscopic membrane, often an ultra-thin film such as silicon nitride, I think, and that this membrane separates the optical cavity into two parts and acts as a beam splitter. So this general type of membrane in the middle optomechanical setup was first implemented by Thompson et al. In 2008, and it has been investigated pretty thoroughly, both theoretically and experimentally since then. So this is just a snapshot of miscellaneous papers on the membrane in the middle setting that I've added here as evidence that this is a very lively field of research. But going back to our thought experiment, how could it be implemented in a membrane in the middle system? Well, preparing the photons in a Fock state or in a thermal state, I'd like to think sort of maintains a close analogy with classical thermodynamics. But if we're going to try and make things a bit more experimentally realistic, we're going to have to include the process of driving the cavity with some lasers. Now, if the cavity is driven on resonance with pulses that are shorter than the tunnelling time, then the driving process and the tunnelling process will occur on separate timescales and so can be considered independently. Which means if we drive the cavity with a short pulse, so that is of length less than lambda to the minus 1, where lambda is the tunnelling time, then that is going to generate a coherent state in the cavity. So if we drive the left-hand side with a short pulse of theta polarised light and the right-hand side with a short pulse of horizontally polarised light, then we're going to end up with a theta polarised coherent state on the left-hand side of the cavity and a horizontally polarised coherent state on the right-hand side of the cavity. Now, from the expression we had before, this means we're going to get an energy transfer of this form, where the fluctuations are just going to be equal to alpha squared, and the average number of photons per gas initially is also going to equal alpha squared, which means we end up with an energy transfer of this form, which we have plotted for some experimental parameters taken from this experimental paper, and this is what we get out. So here we have incorporated the effect of damping, both of the cavity and the membrane, just to try and make the setting a bit more experimentally realistic. You can see for these experimental parameters that the rate of cavity damping is much larger than the rate of the mechanical damping, which means on the time scale greater than 1 over kappa but less than 1 over kappa m, the energy transfer tends to an approximately steady state. You see that the steady state energy transfer is largest for indistinguishable photons, smallest for distinguishable photons, and partially distinguishable photons are midway between the two, as you'd expect from our expression up here. And the energy transfer for indistinguishable photons is of the order of half a megahertz, which corresponds to exciting the mechanical degree of freedom by a single photon, approximately, which is quite a small enhancement in some respects, but actually such small energy transfers are experimentally detectable by a number of different techniques, and you could always enhance this energy transfer by applying a train of pulses. So instead of just having a single pulse coming in, which is what I sketched on the previous slide and what we're plotting for here, you could have a whole series of pulses coming in, and then you'd end up with a large energy transfer, increasing the viability of observing this effect. Right, okay, so I have told you about the thought experiment involving a beam splitter. I have argued that we expect to observe an enhanced energy transfer for indistinguishable photons, and that this is the signature of bosonic bunching. And I've suggested that this could be conceivably experimentally realised in the not so distant future in a membrane in the middle optomechanical system. I am now going to move on to talking about the polarising beam splitter thought experiment, which, as I said before, I'll argue realises more directly a quantum analogue of Gibbs mixing. So the key question for this thought experiment is, how does the work that can be extracted mixing two quantum gases using a polarising beam splitter membrane depend on their distinguishability? And this question is motivated by Gibbs's thought experiment on mixing. So let me just recap that again very quickly. So Gibbs's protocol to extract work from mixing two gases utilised a pair of semi-permeable membranes. So we had a green membrane that was permeable to green molecules but blocked yellow molecules, and a yellow membrane that was permeable to yellow molecules but blocked green molecules. During the mixing process, each gas isothermally expanded to double its initial volume. So if we assume that there was initially n gas molecules in each gas, and they were all at temperature T, then by sort of basic undergraduate thermodynamics, the work done during the two isothermal expansions of each of the gases is just equal to 2n kBT log 2. But this protocol is only possible if the two gases are indeed distinguishable. If they can't be distinguished, then no such semi-permeable membrane can be found, and so no work can be extracted. And indeed, considering only classical homogeneous gases, so that is gases consisting of only particles of the same type, then these are the only two options. So either the particles are distinguishable, in which a pair of semi-permeable membranes can be found, and the work 2n kBT log 2 can be extracted, or the gases are indistinguishable, and then no such membranes can be found, and so no work can be extracted. So in this way, the work jumps discontinuously from 0 up to 2n kBT log 2. But in the quantum regime, the possibility of partially distinguishable quantum states makes things more interesting. So we could suppose that the gas particles are distinguished not by their type, so like their elementary or molecular composition, but rather by their internal state. And then as the overlap between any two quantum states may vary continuously, we expect that the distinguishability of any two quantum gases can also vary continuously, and therefore we'd expect that the work output, in contrast to the classical case, will also vary continuously. So this argument, this was first explicitly recognised by a pair of Soviet scientists, Lubashits and Podgoretsky, back in the 70s. Their argument was formulated in terms of the change in von Neumann entropy associated with mixing two quantum gases. And a more modern argument was put forward for this claim by Alaverdin and Noy van Kritsen in 2006. And their argument was formulated in terms of a Godspring. But both of these approaches are information theoretic approaches which consider optimum general mixing processes without really discussing how one could go about physically realising it. So we thought we could perhaps use the membrane in the middle type setup to study the dynamics of quantum Gibbs mixing a bit more explicitly. So specifically, we recognise that a polarising beam splitter effectively realises a quantum variant of a semi-permeable membrane for photons of different polarizations. So that is, we're going to consider a polarising beam splitter that acts as a mirror for vertically polarised photons, but acts as a beam splitter for horizontally polarised photons, which means it's going to be permeable to horizontally polarised photons, but impermeable to vertically polarised photons. So a bit more mathematically, in contrast to a beam splitter Hamiltonian, where both the horizontally and vertically polarised photons are coupled to one another, here only the horizontally polarised photons are coupled. So at a rate lambda h over 2, a horizontally polarised photon on the left-hand side is annihilated, and a horizontally polarised photon on the right-hand side is created, and vice versa from right to left. But the vertically polarised photons in the two cavities are uncoupled because the mirror, the beam splitter, polarising beam splitter, acts as a mirror for them. And then also now, because the polarizing beam splitter acts as a mirror for vertically polarized photons, but a beam splitter for horizontally polarized photons, we expect that the force exerted per vertically polarized photon on the membrane is going to be greater than the force exerted per horizontally polarized photon, which implies that GV is greater than GH, and we need to take into account that when writing down the optomechanical interaction energy. So now the optomechanical interaction energy is equal to the sum of the force exerted by horizontally polarized photons plus the sum of the force exerted by vertically polarized photons multiplied by the displacement of the membrane. Now, in analogy with the classical mixing scenario, we associate the displacement of the membrane due to mixing with a work output. So you could imagine in the classical Gibbs mixing scenario that the work done on the membrane during the isothermal expansions is stored in the potential energy of the compressed springs. And similarly here, we're going to associate the potential energy of the membrane with a work output. But so in the classical case, the final position of the membranes is constant and well-defined, i.e. they're basically just stuck at the end of the box. Here, because we're dealing with a microscopic membrane that is going to be sensitive to the microscopic dynamics of the photon gases, the membrane is going to oscillate around its final displacement, and there's also going to be some spread to its wave function. So we're going to take our work output to be the potential energy associated with the time average displacement of the membrane, just to take into account that otherwise it would be moving about and there'd be some spread. And we're going to start with the same initial conditions as with the previous thought experiment. So we're going to suppose that all photons on the right-hand side are horizontally polarized, and all photons on the left-hand side are polarized at angle theta. And also, as before, we're going to assume that the membrane and the photons are initially non-interacting, that the number distribution of the two gases are the same, and that the membrane's displacement and momentum initially vanishes. And now, if we let this evolve, the two gases are going to mix in the left-hand side of the cavity, and this is going to result in a displacement of the membrane to the right. We expect that the displacement of the membrane will increase with the amount of distinguishability between the two gases. So if the two gases are perfectly indistinguishable, well, you've just got H on both sides, and so there's going to be no displacement. But as you increase the distinguishability of the gas on the left-hand side from the right-hand side, there'll be more mixing and so a larger displacement. And as we are associating the work output with the displacement, we therefore expect that the work output will increase with distinguishability. And this is indeed what we find. So we calculated the dynamics using the same perturbative approach that I described in the previous thought experiment. And we find that the time average displacement of the membrane is proportional to the average number of photons per gas initially, times sine squared theta, where theta is the distinguishability of the two gases. So that is when theta equals 0, the time average displacement of the membrane vanishes. And for theta is equal to pi over 2, when the two gases are perfectly distinguishable, the displacement of the membrane is at its maximum. And for theta between these two limits, we have that the displacement of the membrane smoothly increases as you ramp up the distinguishability. So you see that in these plots here. Here I am plotting the time average displacement of the membrane normalized by the number of photons per gas initially. I'm also plotting the standard deviation in the displacement of the membrane. So that is the fluctuations in the position of the membrane. So that's what the shading indicates. On the left-hand side, I am plotting Fock state photons. On the right-hand side, I am plotting thermal photons. As you can see, the fluctuations in the displacement membrane are larger for thermal photons than Fock state photons, which is perhaps unsurprising because for thermal photons, the initial fluctuations in photon number also contribute to the eventual fluctuations in the displacement of the piston membrane. Now, as I argued before, we can associate the displacement of the membrane with a work output, and this means that the work output here increases continuously with the distinguishability of the photons, which is in line with prior entropic analyses, but is in contrast to the classical case, which, remember, jumped discontinuously from 0 to its maximum. Also, in contrast to the classical case, we now see that there are going to be large fluctuations in the work output corresponding to the large fluctuations in the displacement of the membrane. And this is perhaps unsurprising because we are now dealing with a microscopic quantum piston, which is going to be very sensitive to the dynamics of the gases. And I'm not going to go into this detail, but we can also observe similar effects if we consider a laser-driven variation of this thought experiment, and if we plot things for more experimentally realistic parameters. So here I've just included a quick plot of the displacement you see for the driven variation. You see that the displacement is largest for perfectly distinguishable gases, vanishes for perfectly indistinguishable gases, but we could also consider partially distinguishable gases where the displacement and therefore the expected work output sits between the two extreme cases. Right, okay, so that's the second thought experiment, which I've argued implements a quantum analogue of Gibbs mixing, where in contrast to the classical case, we see a smooth increase in the work output with distinguishability. And as I argued, it could conceivably be realised in a membrane in the middle type setting, though I should probably mention that it is an open question how realisable this second thought experiment is, even more so than the previous one, because no one has yet to try doing a polarising beam splitter in the middle type optomechanical experiment. So we just don't know quite how amendable the ultra-thin polarising beam splitters people are currently engineering are to this type of setting. Right, okay, so I've introduced two thought experiments that are broadly realisable in a membrane in the middle type setting. I'm just going to try and end with a more general sales pitch for membrane in the middle optomechanics. Because I think these two thought experiments I've suggested are really just sort of the tip of the iceberg of the type of experiments you could conceivably realise in a membrane in the middle type setting. So here are some possible extensions that you could look at. We have largely focused on the coherent dynamics of these settings, but it could be interesting to explore dissipation and thermalization more explicitly. So this could either be done through a more detailed analysis of the dissipative coupling of the cavity mode to the surrounding thermal environment, or you could even perhaps use dye molecules. You can actually, this is what this reference here is, you can use dye molecules to effectively mediate interactions between the photons and their environment, which can result in a more sort of direct control of the thermalization processes. And once you've thought about thermalization more explicitly, you could perhaps look at factors such as thermalization gradients. So you could imagine that, as is probably more physically realistic, that the photons and the membrane are coupled to different reservoirs, and so that there is a temperature gradient between them. Or you could even think about engineering temperature gradients across your cavity, so you could have the two gases at different temperatures. In these two thought experiments, we focused on the linear radiation pressure interaction between the photons and the mechanical degree of freedom, but it's also possible to engineer higher order couplings. So, for example, you can engineer quadratic couplings between the photonic and phononic degrees of freedom. So this has been done in a number of experimental settings. Could be interesting to see whether these quadratic couplings could be used to realise some other thought experiments. Gibbs's original thought experiment used two membranes, and membrane in the middle systems with multiple membranes have also been experimentally realised. So it could be interesting to try and see the effect of incorporating multiple membranes. These could be two polarising beam splitter membranes to engineer something a bit like Gibbs mixing, or it could be two beam splitter membranes and to see what happens. More generally, I argued at the start that many of the key thought experiments in thermodynamics can be framed in terms of gases performing work on a membrane attached to a movable piston. More broadly, one can imagine engineering variants of the membrane in the middle of mechanical setting using alternative types of experiments. And I think this sort of really highlights that the membrane in the middle of mechanical setting has wide-ranging potential, not just as a platform to study distinguishability and mixing, as the two thought experiments we've considered have studied, but also potentially for probing more fundamental relationships between information, heat, and work. Right, okay, so we have, in summary, introduced two thought experiments. The first, using a beam splitter, demonstrates that we expect an enhanced energy transfer to a beam splitter piston membrane for indistinguishable photons due to photonic bunching. This thought experiment can be understood in terms of the back action of the Honger-Mandel effect on a membrane in an optomechanical setting. The second thought experiment switched out the beam splitter for a polarizing beam splitter. And in that case, we argued that the extractable work from mixing two photon gases of different polarizations was expected to vary continuously with distinguishability. We've argued that both of these thought experiments can be thought of not just as thought experiments, but could potentially be realizable in a membrane in the middle type experimental platform. And I've also suggested to you that this platform is not just good for this thought experiment, these thought experiments on mixing and distinguishability, but also I think they have potential to be quite useful to study a broad range of experiments and thought experiments in quantum thermodynamics. Thanks for listening.
Thanks very much, Zoe. Really nice talk. So we have plenty of time for questions, and we've already actually had a couple of questions. And anyone else who has any further questions can just kind of write them in the YouTube chat window. So yeah, we have two questions from Stefan Nimrichter. So the first question he asked was, does the quadratic enhance? So this was sort of asked around when you were introducing the first example, right? So the question is, does the quadratic enhancement survive in the non-perturbative regime, or is it in effect genuine to the weak coupling limit?
So we have looked at the higher order. So we've looked at first and second order couplings in the displacement, and we see the effect to both orders. The second order term is very small as long as the membrane is initially cooled. So it's also, you can think of this experiment purely in the first order limit without needing to take into account higher couplings. But yes, we have found that at least just looking at the first two terms that we still see the effect, but it'll be interesting to look at higher order terms and see whether you get it across the full range. Plausibly it'll have to break down at some point, because I'm not sure you'd expect to see this effect purely classically. So I think you've got to be in a reasonably cool regime. One thing I will say is, I don't know, when we talk about the weak coupling limit, we're not talking about the weak coupling limit in the sense that is often discussed in the optomechanical community. So the weak coupling limit in the optomechanical community is when G is small as compared to damping. We're still assuming that G is large as compared to damping, so that the damping effects are relatively insignificant. But we're just assuming that G is small as compared to lambda, the beam splitter interaction strength, and omega m, so the frequency of the mechanical oscillator, which it is for sort of experimental parameters.
Okay, thanks very much. So Stefan actually had another question, an interesting question. So on the work output to the polarizing beam splitter membrane, is your defined work output to the membrane formally useful energy, in quotes, i.e. did you check what the ergotropy would be?
No, we didn't check. That is the honest answer. And it's a good question how useful it is, because it is hard to think about how you would use it to, say, charge a battery, for example. It's hard to imagine how you'd use it to charge a battery. I'm trying to think. So comparing the classical and quantum case. Okay, so in the classical case, you could imagine in this setting using the isothermal expansions to lift up a weight. You could have a bucket attached that gets lifted up. One could perhaps try and translate our scenario into something along those lines. and try and think about using this setting to raise a weight and therefore demonstrate that you do have a useful energy output. I would have thought it would be possible to do that, at least theoretically. How you'd engineer that physically, God knows. So my intuition is, yes, it's useful energy, though it does have large fluctuations. But no, I've not mathematically proven that.
Okay, thanks. All right, let's move on. Lots of other questions. So, sorry, hold on. So the next question was from Dvira Segal, who asked, can you approach the classical Gibbs mixing work?
No. So this is not an optimum protocol. I mean, it depends on the exact experimental parameters you choose, but it is expected to be far suboptimal, which you could see as a criticism of the approach. On the other hand, even specifying, let alone experimentally implementing an optimum protocol is incredibly demanding. So you could, sort of turning it around, actually see it as noteworthy that we have found a suboptimal experimental scheme in which the same qualitative behavior is observed, i.e. the smooth increase in the work output with distinguishability, without actually demanding an optimal protocol is conducted. So no, but I'm not sure it's a bad thing.
Yeah, no, I mean, and maybe I can just follow up. I mean, what's actually obstructing you from reaching the optimal work in that case? Is it related to the fluctuations that kind of Stefan already alluded to, or is it something else, or is it many things?
So one thing I can point out is the work output in this setting is actually the same whether you start with homogeneous gases on either side. So whether you start with theta polarized photons on the left-hand side and horizontally polarized photons on the right-hand side, or whether you start with inhomogeneous mixtures. So you could imagine starting with cos squared theta H polarized photons on this side and sine squared theta vertically polarized photons on this side. So a mixture of horizontally and vertically polarized photons. Mm-hmm. And in this setting, you'd actually get the same amount of work output. Now, in some ways, it's not a fair comparison because in the classical case, we only consider homogeneous gases, and that would be considering inhomogeneous gases. Nonetheless, if you think about the change in von Neumann entropy, you would expect to be able to extract more work starting with the homogeneous case, so with the pure state on the side, rather than starting with the mixture.
Yeah.
Which suggests that there is a bunch of work associated with coherence that this protocol doesn't extract. So that's one way in which our protocol is suboptimal. The other one is we are only considering a single membrane. So our photons only mix on the left-hand side of the cavity. So there's not a complete mixture. Whereas in the classical case, you get a full mixture. So if you use two membranes, you would be able to ramp it up and get some more mixing going on. But I think that's a less interesting question. The more interesting question is how can you access the work output associated with the coherence of the initial state.
Thanks. That's really interesting. Okay, so let's move on to the next question from Nathan Myers, who says, very interesting talk. Thank you. You discussed how the theta parameter varies between 0 and pi over 2, going from indistinguishable to distinguishable. Could an anti-bunching effect be realized with theta equals pi to mimic fermionic behavior? And how do you think this would change the results?
I don't know, but that's a great question because I wanted to try and look at fermionic behavior within this setting. And I hadn't actually thought of doing it by playing around with the polarization. I was picturing needing to actively start with some kind of fermionic system. But if you go back to this picture, the expectation is with anti-bunching, you're going to get fewer fluctuations and a lower energy transfer. That's your intuition. How it works out mathematically, I don't know.
Okay.
But it would be great to look at.
Okay, so more questions. So the next question is from Ben Morris, who says, it seems in your work you have taken indistinguishability to mean the degree to which two states are objectively distinguished as opposed to subjectively distinguished relative. Is this in a question? Yeah, sorry, it is. So you've taken this indistinguishability to mean the degree to which two states are objectively distinguished as opposed to subjectively distinguished relative to an experimenter. What is the motivation for this choice? Smiley face.
So I know he's currently got a project on this, which is why he's asking it. I'm not sure I agree that this is. Also, you could also objectively. So, okay, fine. I've looked at an objective distinction, but an experimentalist, just get yourself a polarizer, and you'd also be able to subjectively, with your polarizer, distinguish between these photons. So I'm not sure there is a distinction here. I mean, maybe he's thought about this more in the context of the project that he's busy writing up right now. But I'd have thought they're one and the same. You got these photons are both objectively and subjectively distinguished by the polarization degree of freedom.
Right. Well, I mean, things that are objectively the case are also subjectively the case for people that aren't wrong. Yeah. But the question, I mean, it's harder to go the other way, right? If something is subjective, it may not be considered objective. But I guess we're straying a little bit too much into metaphysics or something here. I don't even know enough about philosophy to know which branch we're kind of ignorantly.
But given the situation, could have framed it in terms of subjectively distinguishable. So I think I probably need to chat with Ben about this afterwards and dig more into what exactly he's meaning here.
Okay.
Unless he's clarified has he clarified at all?
No, but there's a delay, so it's probably that doesn't. Oh, okay, no, he has clarified. So he says, just to clarify, in your setup, it would be comparing mixing when one uses a polarizing beam splitter to a non-polarizing beam splitter.
So I think the point he's making is that using a polarizing beam splitter is like trying to extract work when you know how to distinguish them. So the point is, if you know they're distinguished by their polarization, you can use a polarizing beam splitter and then get your work output. When you're using a beam splitter, it's like you're trying to get some thermodynamic output, but you don't actually know how they're distinguished. And so it's quite funky that you get this enhanced energy transfer without actually knowing how to go about distinguishing the photons. So I think the point he's making is that the PBS case is where you subjectively know how to distinguish them, but the first case with a beam splitter is when they are objectively distinguishable, but subjectively you don't actually know this. So I think I considered both cases. What was his question again?
It was just why you choose objectively distinguished as opposed to subjectively distinguished states or particles.
Well, I think I now consider both cases, but fine. I probably need to chat with Ben about this another time.
Yeah, I'm getting a bit confused. So maybe you guys can continue this one in person or in private. So there's another question from Michael Moskalets, who says, "Thank you for a nice talk. When exactly is the work is extracted? I mean, when the superposition state is projected into the states with definite number of particles at each side of a membrane."
Oh, I have some slides on this if he's asking what I think he's asking. So here, all I'm talking about is the energy transfer to the membrane. Mm-hmm. And one thing you could ask is this energy transfer heat-like or work-like? And now, because... Okay, so I don't want to sort of dive too much into this question because it's a wormhole that lots of people have written about. But sort of the instinctual answer is that this energy transfer is more heat-like than work-like because it arises from fluctuations in the displacement of the membrane. Mm-hmm. So the average displacement of the membrane vanishes, unlike in the second PBS example where we talk about work. Here, the average displacement vanishes, and so the energy transfer purely arises from fluctuations. So in that sense, the energy transfer in its raw form seems to be heat-like. But you could imagine doing a Szilard-type protocol to extract some work. At any moment in time, you've basically got this superposition state for indistinguishable photons, where you've got a superposition between there being more photons on the right and the membrane being displaced to the left, and there being more photons on the left and the membrane being displaced to the right. Mm-hmm. But suppose you were to perform a measurement on the number of photons on either side, Then you are going to collapse the superposition, ending up with a well-defined photon number imbalance and a well-defined displacement to the membrane. And that well-defined displacement to the membrane can be associated with a work output. And so this kind of Szilard type work extraction protocol converts your heat-like energy transfer into a work output. So I guess in the more direct answer to his question, I'd emphasize that the energy transfer in itself is not a work output, but perhaps you could do a Szilard type protocol to try and convert it into a work output.
Okay, thanks. That's really interesting. So I think that was it for the questions. There's lots of people clapping emojis, obviously, and saying thank you for a very nice talk.
They're also home by themselves. You never know.
Say again, sorry. Well, they could have, yeah, hopefully they were also clapping in real life, yeah, just to make it feel more real for themselves.
Yeah.
But I think I got all the questions there. We had pretty lively discussion, I think. So, no, there's one more question. So there's a question from Yunjiao Wang, who says, really cool talk. Is it possible for us to implement a one-sided permeable membrane for photons for Feynman's ratchet?
Okay. So those examples was me largely just throwing things out to the community as ideas to things to think about. So you could think about doing it using electromagnetic induced transparency type ideas, interference effects. That might, so I've not got this fully fleshed out as thought, but one might think about trying to use interference effects so that effectively photons can only go in one direction. More concretely related to that scenario, so thinking about the Szilard engine, Robert Aletsky has he doesn't like understanding the Szilard engine and Landau erasure in terms of information thematic ideas. He likes to think that work is required in order to stabilize the membrane on one half or the other half of the cavity. So one thing you could look at in this kind of scenario is how the idea is that at higher temperatures, there'll be more spread to the membrane in the middle. And so more work will be required in order to stabilize, in order to confine the particle in one half or the other. So you could perhaps in this setting look at the trade-off between the temperature of the membrane and the amount of work required in order to confine the particle to one half of the membrane. So you'd sort of end up with a work meter where the displacement of the membrane would depend on the spread of the wave function for the membrane. And so, yeah, this is something I talked to Robert Aletsky about a while ago. He's got this relationship between the work required to confine a particle and the temperature of the membrane. And I was wondering whether you could use this setting as a means of measuring that. And that is directly related to Feynman's ratchet because when you try and resolve Feynman's ratchet, you need to take into account basically the work costs of physically modeling the membrane to actually confine the particle in one half. So in terms of the direct question of whether you could implement this unidirectional membrane, whether you could have this sort of valved membrane in a membrane in the middle type setting, I'm not sure. But could you look at aspects of that thought experiment within the membrane of the middle setting? Yes, I think you could.
Okay, great. Thanks very much. So yeah, I think that really is it for questions. So thanks to everyone for tuning in and participating in such a nice, lively discussion. And especially thank you so much, Dr. Zoe Holmes, for a really interesting talk.